Of course, thanks to the organizers for the invitation. And thanks to Ian Granovsky for writing the first 30 seconds of my talk as the title of a paper 30 years ago. All right. So what I want to talk about today is how you can understand certain ideas about the representation theory of the symmetric group and various generalizations of it in terms of categorical actions. The thinking about this way kind of unifies the ideas, simplifies everything, lets you put everything in a nice combinatorial frame, which is, of course, the idea that affine SLB had kind of controls. So how does this control work? Well, blocks of the symmetric group correspond to weight spaces for representation of SLB. So I can write this here. Maybe I should have added here. If I look at the K group, the space of formal span of projected modules over Fp of Sm, then that corresponds to a particular simple module, V lambda 0, over the affine Lie algebra SLP hat. And so representations break up as a direct sum of weight spaces. Categories break up as a direct sum of blocks. Those two decompositions are the same. Every block of the symmetric group, and this is for all n at once, corresponds to a weight space of V lambda 0. So for example, the highest weight space corresponds to the only block of S0. The way this correspondence works is you index representations, for example, simple representations by P regular partitions, and the corresponding weight you subtract the simple roots of SLP hat once for every box of residue I in the partition. So lots of nice statistics actually have good interpretations in Lie theory. So one thing that comes up a lot in the representation theory of symmetric groups and related objects and characters P is the number of I addable boxes minus the number of I removable boxes. That's taking the weight and taking its inner product with AI check. So yes, that plays a very important role in the structure of representations. This tells you for the SL2 generated by the EI and FI corresponding to that simple root, what weight do you have? That's what AI check means. And then finally, a block has a defect K. So this is often called weight in representation theory of the symmetric group, but I think I found enough sources that call it defect, but obviously it's very bad if you call it weight, because then it gets confusing with SLP weights. So I'll say defect. And that corresponds to which orbit of the affine file group you're in. And I'll just note here, this delta, so this is the imaginary root. It's invariant under every reflection in the affine file group, so it doesn't actually matter whether I subtract K delta before or after. It's here or C's. All right, are there any questions?
Can you remind us what defect means?
So, I mean, the important thing is it tells you what orbit of the affine file group. In terms of the representation theory of the symmetric group, it's basically the number of times you can remove a P hook from the P regular partition. The P core has defect 0, and then every time you add a P hook. So similarly, right, in this representation theory, you would say for every weight space, you can add delta to it and see if you get a non-zero weight space. And after you do that enough times, eventually you'll get to something that's not a weight space. This lambda 0, because it's a fundamental weight, like the last guy before you become empty, is exactly the stuff in the orbits of latest zeros. The p cores correspond to the stuff in the Weyl group orbits of the highest weight.
So,
Yes.
can you scroll up just a little bit? So, is lambda zero chosen, or it's like
It's the fundamental weight.
it's the
It's defined by alpha 0 check of alpha 0 equals 1 and alpha I check 0 equals 0. Right? So I told you that it's the number of addable boxes of a content minus the number of removable boxes of a content. So if I have an empty partition, I have one addable box and it has content 0. So that's why I get the highest weight vector with this one. All right. Any other questions? Okay. So there's a theorem of Chuang and Rouquier, which I at least discussed. I certainly didn't prove in full generality last week in my talks in the workshop. That if I take two blocks of the symmetric group with the same defect, then they're derived equivalents, they're derived categories are equivalent. And well, since these guys are in the same Weyl group orbit, I just have to show this for generators of the Weyl. So I only need to show this for simple reflections. And Chuang and Rouquier do this by writing down an explicit complex. I was maybe a little, this is maybe a little opaque to people who were not here for my lectures last week. Maybe I'll just say this very quickly. Here, EI is the EIs are summons of the restriction. And the FIs are summons of induction. And in terms of working with partitions, restriction adds a box, induction removes a box. And this breaks up the functor according to what the content box you're adding is. Or alternately, by looking at the eigenvalues of the uses of equivalence. All right. So I write down a complex that's built out of induction and restriction. That's not going to matter very much. Exactly what these functors are. The only thing that's important about them is that they act on the Grothendieck group by the Chevalier generators of the I. As well. A0 FpSm by affine TI, the usual Chevalier generators acting as representation. So this is a great theorem. But some of us don't really like derived categories. Not me, I like them, but they're, you know, they can be a little annoying. So you might wonder, why not need derived categories? Do I always need derived categories? I mean, I know some examples where if I look at the P cores, the corresponding block is just equivalent to copy of the category of K vector spaces, and those are all equivalent to abelian categories. And actually, you can check that all the blocks of defect 1 are equivalent to abelian categories as well. So maybe I don't really need this. I mean, I do kind of need the derived thing, but I maybe don't need it that bad. So I'm going to get an equivalence of abelian categories. Theta I is going to be an exact functor on abelian categories. So on derived categories, we can call it T exact. If when I look at my lambda weight space, I look at the action of EI and F, it's all the vectors in the space. It's feedback. All right. So why is this the case?
Wait, sorry, I'm trying to get this in.
Okay, so question, when is theta I an equivalence of abelian categories? answer when this category that I'm starting with, right, the OneNote has the disadvantage that it doesn't have one. When this category here is highest weight, corresponds to a weight space where every vector is highest weight for the corresponding SL2 action.
For the SL2 action.
Yes. So look at this complex. I have one term that's FIs, and then all the other terms start with an EI. So if a vector is a highest weight vector, if it's killed by the functor EI, then all these higher terms will act by 0. And only this guy in degrees will act in a non-trivial way. All right, so if, let me just write this. And I should mention, I mean, this fact is was surely known to Chuang and Rouquier when they wrote their paper. I don't think they ever really explicitly wrote it, but it was probably because they thought it was too obvious to mention. In this case, what happens is that I have lambda, I have SI lambda, and in one direction, I have the divided power of Fk. The other direction, I have the divided power of Pk, and I should have eyes on these. And these are inverse equivalences of categories. And you can check that this is true if and only if everything here is killed by EI.
And is this for all K or for what's K?
K is, oh, did I switch? Sorry. Sorry, it should have been N. So it's the number of times I have to act to get to the image under the bottom, right? The fact that I told you it's going to S lambda tells you what it has to be, because there's only one power of this guy that goes to the right weight space. So yes, these should have been M's. All right, and this happens if when I try to go any further on this SL2 string, I get to 0. Right? So the inverse functor has the opposite property, that there's only one term that doesn't start with an FI. Or only one term that doesn't start with going too far that way. Okay. So sometimes this happens and sometimes it doesn't.
You said this is an if and only if.
This is if and only if, yes. Right. So yeah, I'll just say.
So yeah, that's not true. The equivalence is entering the complex, and once you enter the complex, you're not.
Well, yeah, I was about to get to this. Okay. So it's clear that one term acts non-trivially. Chuang and Rouquier proved the converse, and the way they prove the converse is that if you act on any weight space that's not the highest weight space of, if you act on this something of this weight and it's not highest weight, they actually show that there's sort of a symbol that goes to a shift of a symbol, right? It's perverse, and the perversity tells you that it can't be T-exact. I should mention this is used, but in a slightly not explained very well way in a paper of Amara and Sheps. And there's even sort of a slightly exceptional case that's maybe worth knowing about. Just to mention, there are cases where this theta I will be a shift of an equivalence of abelian categories. So we'll send every module to a shift of a module by some fixed R. And when this happens is when you're not a highest weight space, but if you sort of start at the highest weight space, and go down here, this map is an isomorphism. So this happens when all the root strings through your weight space are the same length, but you're not at the end of them. So this just happens occasionally. And this again follows from Chuang and Rouquier, but they sort of basically you have to be a bunch of the same minimal categorification put together, and you know what you shift by in the minimal categorification. All right, are there any questions?
Say odd cases, do you mean odd as in strange or odd as?
Strange, yes, unusual. Weird. All right. So, yes,
So do you get these beta I for breaking the SL2 structure, or do you need?
yes. There's no extra, like, nothing I am saying here is special about the symmetric group. This is all just a statement about having SL2 connections.
When the theta I is equivalent to the theta category, is the answer for this particular example.
Sorry?
Like your answer to this question is about this particular example.
No, it's just any height.
No, and for any SL2 categorification,
Take some simple categorification.
then this weird, unusual case applies. I mean, it's on a simple categorification, if you're not in the highest weight, it's not T exact, it's the shift of something T exact. Okay. But that's a case where all the root strings going through there are the same length, even though you're not at the end of it. So that's, I even had to explain this so people wouldn't ask that question. All right, anyways. All right, so this sounds a little unusual, right? Like, how often are you looking, the highest weight space, is that really that interesting? But actually, if you think about this case of the symmetric group, and you're comparing two blocks that are far away from each other, almost all of the time you will be in this case where you are the highest and lowest weight. Sounds weird, but if you sort of think carefully about the affine Lie algebra, this just pops out at you immediately. It comes from the fact that if you have a weight space, there are only finitely many positive roots that you can add to it and go to a non-zero weight space. If you're in a simple highest weight representation of an affine Lie algebra. The way I like to think about this is using what's called the alcove picture. So I'm gonna specialize the case SLE hat, like SLP hat even. Though again, everything I'm going to say basically applies to any affine Lie algebra. So the fundamental alcove, if I didn't have this inequality, this would be the dominant Weyl chain. Right? X1 is greater than X2 is greater than XE. So making it the alcove is I add in the additional restriction that XE is greater than or equal to X1 minus 1. Right? And the picture you should have here, right? This is the SL3 hat picture. So here are the boundaries of the dominant Weyl chamber for SL3. I add in another restriction, which is this hyperplane. All right, because I'm doing things over SLE, I take this guy in R to the E and I mod out by all the constant vectors. Okay. So if I have any dominant weight, I can try to define a bijection between the orbit of this guy under the Weyl group and alcoves. So alcoves are the pictures here. They're the images of the fundamental alcove under the action of the affine Weyl group. But if you don't sort of know the story, I would just concentrate on this picture. So you're taking the positive roots of SLE, of in this case SL3, but in general SLE, and you're looking at all the hyperplanes where they take on integer values, and you're cutting the dual carton up into those chambers. All right, so I can associate weight spaces of my representation to alcoves. And the affine Weyl group acts freely transitively on alcoves. So if it acts freely transitively on this orbit, then this is going to work out great. Every element of my orbit would be W times mu for some unique W, and I look at W inverse times the fundamental alcove. Now, unfortunately, mu might have some stabilizer. So then I'm going to choose my W with minimal length. And what that's going to mean here is I don't get every alcove. I only get the ones that sit in the dominant Weyl chamber for the stabilizer of it. And this is relevant because this happens for the case of the symmetric group. Now you might wonder, why am I putting this W inverse here? Somehow when you do this kind of theory, you have to kind of insert inverses at slightly random places that are hard to remember. But there is a really good reason to do this. So when I want to compare two weight spaces using this Chuang and Rouquier guy, I want them to differ by multiplication by a simple reflection. But if I act on alcoves in the obvious way, then guys who are differ under simple reflection might be really far apart, right? If I start down here and I apply this simple reflection, I'm going to end up all the way over here. So what that inverse does is it fixes that problem, right? So when two guys differ by multiplication by a simple reflection, their corresponding alcoves are adjacent because they're gotten by taking the fundamental alcove and the image of the fundamental alcove under that reflection and translating both of them by W. And I can even say what they're going to be adjacent across. They're adjacent across the hyperplane defined by the vanishing set of the root W inverse of alpha I. So for example, if I have E equals 3 and I want lambda to be this element of the affine Weyl group times mu, then what do I see? Well, mu is going to, I'm now going to look at the image of it under S mu, that is S0 mu. So that means I apply S0 inverse to the fundamental alcove, same as S0. I flip over this guy, right? Now I want to look at S1, S0 mu. So I apply the inverse of that. I apply the same reflections, but in the opposite order. So I flip over S1, then I flip over S0. And you see here, I went over this hyperplane, and this is not one of the simple root hyperplanes. Right? It's when this simple root takes on value 1. Right? And then if I have S2, S1, S0 mu, I do those in the opposite order. I'm going to go all over the place, but then I end up here. Right? I went across this hyperplane. So this reduced expression I can think of as a walk in this alcove picture. And every time I apply one of my simple reflections going from mu to lambda, right? If I want my derived equivalence from the block for mu to the block for lambda, I'm applying theta 0, theta 1, theta 2, theta 1. And every one of those steps corresponds to crossing one hyperplane here. And which hyperplane I cross has a nice kind of explanation. Okay, so now what does this idea of I'm on a highest weight space look like from this perspective? I'm looking at lambda equals W mu. And I'm going to look at, well, is it true that when I go up by EI, I get a non-zero weight space or a zero weight space? That's the only thing I need to know to find out whether theta I is an abelian equivalence of categories. Well, I can look at this weight space, but I can also look at its image under any element of the affine Weyl. So I can take lambda plus alpha I, and I can apply W inverse. And I find this is the same as the question of I take mu and I add W inverse alpha I. And I ask, is that a non-zero weight space? So I just want to go back to my picture. Remember, each reflection corresponds to crossing one hyperplane, and the hyperplane involved is exactly W inverse times alpha I. Right? So, for example, you know, this is S1, S2, S1 applied to alpha 0, check equals 0. Similarly for all these other hyperplanes I crossed. I must have that. Sorry. I think it's yeah, I'll screw it up. There's always inverses involved, right? I'm crossing alpha check equals 0. So the next one I'm crossing had better be S0 times alpha 1 check equals 0. This guy. And then the next one had better be S0, S1, 2, etc. Okay, cool. All right. So the important thing is whether I get a T-exact equivalence only depends on which hyperplane it is. Didn't matter what chamber it was. Any two pairs of chambers that are adjacent across the same hyperplane, I would always get the same answer about whether the Chuang and Rouquier functor is exact or not. So we have a distinguished set of hyperplanes that are the bad hyperplanes that keep me from having abelian equivalences. And I call these Scopes walls, and the chambers that they cut out Scopes chambers. That's building on work from over 30 years ago by Chuang and Scopes about how to find these Morita equivalences between blocks of the symmetric group. Yeah, are there any questions? So the important thing here is the only thing I ever need to know is whether particular weight spaces are non-zero. And I can answer that question by translating everything to the dominant Lyle channel. And the price I pay is I'm looking at a single dominant weight that tells me about everything in the orbit, but I have to look at adding all the different positive groups to it. But that's the only thing I need to check. And so in particular, there are only finitely many of these Scopes walls if my block categorifies a highest weight representation. Because there are only sort of finitely many affine roots I can go up by and get a non-zero weight space.
Right, so the Scopes, I'm trying to figure out whether it's a good or bad thing. The Scopes walls are the ones that if you cross it, you're not.
Yes. There are finitely many affine roots where if you cross them, it's not an equivalence of abelian categories. And in all the other cases, it is. So I was going to get to the examples. Now let me actually skip past that for a moment. So this is the case if I look at defect 3 blocks of F3. So this picture is on SL3 graph paper because I'm working in characteristic 3, and so everything is about SL3 hat. And then the defect group tells me how many walls I need here. So the higher the defect is, the more times I have to go up, the more positive roots I can get non-zero weight spaces when I go up by. So in this case, right, I have all of these different walls that correspond to different equivalences between blocks, but there are only 6 of them that actually don't give you an equivalence of abelian categories. And what I've written here, this probably looks a little indecipherable. These are the Cartan matrices for the Hecke algebras of roots of unity. Those are easier to calculate than the Cartan matrices for blocks of F3, and they reveal the same thing. You can check just looking at the diagonal entries, all of these Cartan matrices are different. None of these abelian categories are the same. But I'm just showing you a selection of different possible chambers. There was room to put the Cartan matrices for all of them. And if I had, you would have noticed some that were the same because I have a tensor with a sign representation. So these categories are actually equivalent as abelian categories, but not through these Chuang and Rouquier things. All right.
And so the statement that they need stuff in every alcove, but if you're in the same scope chamber, then you're.
Yeah. So oh no, I thought I was do not disturb. I don't even know what that notification was. It's probably better if I don't look. All right. So every alcove here corresponds to a block of F3Sn for some n. So I gave you some examples here, right? So with every alcove, there's a W that sends it back to the fundamental alcove, and you act on lambda 0 minus, in this case, 3 times delta with that element, and you get some weight space, and there's a block corresponding to that. So what I'm drawing here are the 3 cores that correspond to these chambers. So I'm looking at the blocks where I take these 3 cores and I add 9 boxes to them, 3 hooks.
These matrices are telling us dimensions of Hom spaces?
Yes, these are the Cartan matrices, so the dimensions of Hom spaces between indecomposable projectives. So for example, you might look here and say, oh, there's one indecomposable projective here, whose endomorphisms are 10-dimensional, whereas there are 2 different ones here, and there are 0 here. So none of these categories are equivalent, and these ones that have 2 10s, I did check, there's something that distinguishes them. This guy has a 4, and I think this one doesn't. Right, so you can actually check. None of these categories are equivalent to each other. And it's exactly that going from here to here is cross one of these walls. So once I'm here, all of the blocks corresponding to these guys are all equivalent to each other. And all of these guys are all equivalent to each other.
So the things here are restricted partitions. That's it.
Yeah.
And then is there, I mean, is there a like combinatorial restriction for whether it's an equivalence part? Just for partition?
You probably could. It would be a little bit messy. No, he was talking about the equivalence classes, like, you know, the whole chamber.
Scopes it down to the smallest core.
Yeah.
So think it's good.
Because that's the number of simples in the block, hopefully. It might be Sage lied to me. You know, Sage has been known to lie sometimes, so yeah. I mean, you know, it's right. I'm looking at adding 3. So I'm looking at like 3 partitions with 3 boxes, and hopefully there are 9 of those.
I think the matrix is like a 10 by 10.
Yeah, it's.
Oh, okay. Yeah, you're right. There are 10 by 10. Okay, well, hopefully there are 10 of those then. All right, and I sort of skipped by this, so let me just say, and it was, you know, proven by Scopes in slightly different language that if you have blocks of FpSn and FpSm that are in the same W orbit, so they have the same defect group. Whoops, I missed a closed parenthesis there. And their chambers, their alcoves are in the same chamber, then they're equivalent as abelian categories. In particular, since there are only finitely many chambers here, there are only finitely many abelian categories up to equivalence that show up as blocks of FpSn with a given defect group. All right.
That wasn't an if and only if statement.
No. In fact, it is the converse is false. Precisely because if I tensor with the sign rep, I reflect across this picture. These 2 blocks are equivalent, and they're not in the same chamber. It's an interesting question whether there are any other exceptions after that. But all right. Now I sort of was explaining this about the symmetric groups because that's a nice concrete example where the answer was already known, but exactly the same principle applies to any other categorical action, literally with the same proof. Right? Once you know this is a statement about SL2 categorifications, it's just a statement about, well, I look at this SL2 categorification and I look at what the non-zero weight spaces are. So for example, instead of looking at the symmetric group or the Hecke algebra, I mean, for one thing, I could look at the Hecke algebra and the combinatorics is exactly the same, but I could look at the Schur algebra or Q-Schur algebra, and now every block is going to be a quasi-hereditary cover. So the Schur algebra is a quasi-hereditary cover of the representations of FpSm. So that tells us that the weight spaces that have non-zero multiplicity are the same, right? Every non-zero block of the Schur algebra corresponds to a non-zero block of FpSm. So the Scopes chambers are the same. And the Chuang and Rouquier functor is an equivalence between blocks of FpSm, if and only if it's an equivalence of abelian categories between blocks of the Schur algebra. So there's a natural extension, which is to look at Ariki-Koike algebras or cyclotomic affine Hecke algebras, depending on your preferences. I won't define these for want of time, but they're a generalization of the symmetric group where you essentially throw in extra polynomial generator. They were in Vanessa's talk. In particular, they involve imposing a polynomial relation on, what was the symbol you used for it? Was it T0?
Yeah, I used T0.
Okay, so.
Oh, no, yeah.
Okay, applying this polynomial relation to T0, which I mean was something Vanessa did in her talk to get the finite Hecke algebra as a quotient of the affine. So the module categories over these categorify other simple modules over SLP. And you can get any highest weight simple module over SLP hat by taking the right polynomial. Now, life is much more complicated in many ways when you do this. In particular, there's more than one dominant weight space under, adding delta. So there are more orbits you have to worry about. And notions like core and such get more complicated. But it's really not too bad. I think I don't want to do this detail in super detail. Like I said, my slides are on the web, or you can find this exact same example in my paper. But in P equals 2, we can actually very easily figure out what all these Scopes walls are for any M0. And it's actually not very hard. The key thing is we have to look at a dominant weight. We're going to look at the orbit under that dominant weight, and there will be more than one of those, right? So, all right, I think I'm just going to go past this. We end up with an explicit formula for the Scopes walls in terms of the number of boxes, which is like a tiny bit complicated. So there's sort of a generic version of it when M1 and M0 are both non-zero, where it's just the minimum of the number of boxes of content 0, the number of content 1 plus 1 or minus 1. And this is, if you think about the number of boxes in the partition, this is kind of the most obvious bound you can come up with. But that bound actually doesn't quite work if M0 or M1 is non-zero. So for example, let's look at B0 equals B1 equals 3, M0 equals 12, and M1 equals 0. And I picked this 12 because what am I going to be looking at for my Ariki-Koike algebra? I'm going to be looking at 12 partitions. So 12 tuples of partitions with 6 boxes. There's going to be an incredible number of those. It's going to hurt, it would kill your computer to try to enumerate all of this. But you don't need to. It's all just stuff about the representation theory of SL2 happening. So I can just look at these formulas and immediately read off what the Scopes walls are. So in this case, they're when the statistic x1 minus x2 takes on the values -2, -1, 0, 1, 2, and 3. And it's always that for each of my simple roots, I have some number of consecutive integral translates. It's just exactly which integral translates I get depends on the details of my representation. So in this case, I have the fundamental alcove here, and I have representatives of my chambers. Here's S1 times that, here's S0. And again, you see this thing about going adjacent, it means putting the reflection at the end, at the start rather than the end. So S0, S0, S1, S0, S1, S0, A, etc. And I realize I forgot to define something. So when you look at this picture, obviously there's one chamber that attracts your eye. That seems way more impressive than the others. It's just bigger. So what's always going to happen, because I have finitely many integral translates of each weight, I'm going to have one big chamber, which is I'm on the same side of all translates of one weight. I'm going to have one of those for every Weyl chamber. And those are what are called RoCK blocks, where RoCK is for Rouquier, Chuang, Kessler. So this is sort of the biggest equivalence class of these. For FpSm, there's only one because I'm forced to be in this dominant Weyl chamber. But in general, there will be more. In fact, you see that here in this SL2 case. Yeah. So I can have a RoCK chamber here, a RoCK chamber here. I think I'm actually lying if I unfortunately adjusted this example a few too many times. So this is a small lie. But if my M0 and M1 were non-zero, then I would have two different classes of RoCK blocks that wouldn't have to be the same, corresponding to the two.
In this example?
I mean, you could say the defect is 3. I'm not totally sure what you mean by defect.
Wait.
But like what? I mean, yes, it's 3. Yes. So yeah, in this context, that means the number of times you can add delta before you get to a 0 weight space. And so yeah, it's 3 because I can remove 3 2 hooks from anything. Or well, it's actually a little more complicated, right? What do I mean by 2 hooks? That's not literally true, but there are things in here I can remove 3 2 hooks from. So it's yeah, defect 3. All right.
So why you're only considered dominant chamber, but not your like
Because of this fact. When I was doing FpSm, I had a highest weight that had a big stabilizer. It had a whole copy of the finite Weyl group as a stabilizer. So everything was going to lie in a dominant chamber for the finite Weyl group. Whereas if I take a generic dominant weight, it's not going to have any stabilizer. It just happens that because the fundamental representations are so small, there aren't any dominant weights with no stabilizer. And you know, the way you see that here, right, is if I write a minimal expression here, it can't start with anything but S0. So when I do this alcove walk, I have to go this way. I can't go any of the other directions. But if I were in some more generic representation, I could. You. Okay. All right, so P equals 2 we can do by hand. For other types, it's much better to have Sage do it, assuming that Sage doesn't lie to us. And well, it's hard to be sure, but I hope I've checked this program enough times. So I wrote some Sage code where you can just pop in what your multi-charge is. And I just want you to know here, I put in absolutely enormous multi-partition, right? So I'm looking at 3 partitions. My multi-charge has 3 things in it. And I'm looking at ones that roughly have 150 boxes in them. So again, this would be totally impossible to enumerate by hand. There is no way you would consider doing this. But because we sort of think about things in terms of SL3 hat, it just turns into simple inequalities. And the computer can very, in half a second, does out, well, is this guy RoCK? And the answer is no. And you'll see this, there's a problem. So what it's looking at is for each simple root, there are finitely many translates that are the scopes walls. And if I'm going to be RoCK, I have to be on the far side of all of those. So there will be some values that my inner product with a particular simple root can't be between. So here, I ended up between these 2 values. Life is rough. So these values being big tells me this is sort of a block with a big defect. And there are a lot of walls I have to cross that won't be equivalences of categories. And to see how sort of sensitive this is, I changed one number here. I changed 58 to 59. And suddenly everything got much better. So these numbers got much smaller. I moved into a block where there are many fewer of these walls. But there's still one causing me trouble. So what this is looking at is all the translates of one simple root. Well, there's no problem there. All the translates of another simple root, no problem there. But this one there's a problem with. So I'm a little bit stuck.
What are the numbers?
Sorry. Oh, sorry. Yeah, maybe I've gotten too used to this. This is telling me the number of boxes of different residues I want. So this means I look at 3 partitions with charges 1, 1, and 0. And I want 45 boxes with residue 0, 58 boxes with residue 1, and 53 boxes with residue 2. So I would not want to try to enumerate all the partitions with those properties. That would be very bad, but I don't have to. Because all that matters is whether there are partitions with a given number of boxes. And you can find that purely from looking at the Weyl polytopes of SLP hat representations. All right. Are there any questions? Yeah.
There was something that I missed earlier, now I can maybe understand. You said it for this affine one example, that all the walls are consecutive.
Yes.
And is that true in SL3 as well? Like the walls are consecutive?
Yes. Yes, this is true for all SLNs. And I mean, this is basically like, if you look at 2 roots, they generate an SL2 hat, and you do the calculation for SL2 hat. All right. Yes.
You don't have a notion of being on a wall, everything's in and out there.
Yeah. Yeah. Yeah, this is about when I compare 2 alcoves, do I get an equivalence of abelian categories or not? And I don't if I can tell you exactly which hyperplanes that doesn't happen. And there's a finite list of them. All right, I'm running low on time, but there was one other thing I wanted to talk about. So this is all in a paper on the archive. Hopefully it's all carefully checked, but there is also sort of a speculative thing I wanted to bring up. So one thing that I think is sort of bothering people about this RoCK story for Ariki-Koike algebras, more general things is, so the reason that Chuang and Rouquier have their name attached to RoCK blocks is that they gave a sort of nice description of the RoCK blocks as an abelian category. as the principal block of the representations of a wreath product. And I think this is only in the case where the defect group is abelian. And for Ariki-Koike algebras, it's not so clear how to generalize that. But I think I actually have an idea about how to do this. So, somehow there is this annoying thing, as Chris said, somehow there are all these separate alcoves and none is better than any other. There's no reason that I like this guy better than this guy. But I want sort of one description of this category. It's annoying that all of these give me the same abelian category, and I don't know what it is. But maybe I know what it is.
Sorry, so Chuang and Kessler said they describe the rock blocks of which
Of FpSm,
oh, okay.
I think only in the abelian defect group case. So only when, yeah. Yeah. Oh, but there's only one for FpSm because of this thing about being in the dominant alcove. So there's only one option there. Okay. So I'm very short on time, so I apologize to people who don't know this story, but I think there are enough people here who do that it's worth mentioning. So if I want to look at FpSn, where E is prime, or a hack algebra at a root of unity, an ETH root of unity, of course, I can write that as a KLR algebra for SLE hat. And that's gotten by writing down these kind of diagrams with labels being from the SLE hat Dinkin diagram identified with F, with the FE, so FP, or with the ETH roots of unity, with the usual relations, which again, I'll just go by, I don't have much time, with the cyclotomic relations. So if I want the group algebra of Sn, I say that if I have any label other than 0 at the far left, I get 0. And if I put a dot on a strand with 0, I get 0. This is the cyclotomic quotient relation. More generally, for the Ariki-Koike algebra, I would put mi dots on a length strand with label I is 0. All right, well, that's cool. But I'm going to change how I write these relations. And, those of you who know me know that this is always what I want to do. I want to add in a red strand. I want to add in the relation that if I make a bigone with the red strand, straightening that adds mi dots. And then I want to add in the relation that putting a black strand left of the red one gives me 0. So this has exactly the same effect as the relations I put earlier. And this just seems kind of like a silly thing to do, like making life more complicated. But
So Ben, did you want to have mi dots in the left picture? You have mi dots in one, but only one red.
no, right? The point is, this guy is 0 because it has a black strand to the left. So that tells me that having a strand here with mi dots is 0.
But not one dot. Like normally it's the number of red strands is the number of dots. Then you've got more dots.
Well, you can think of it as mi red strands together.
Okay. Sorry.
Yeah. There are variations on this. I also don't know exactly when I'm supposed to be stopping. Okay, I'll finish up quickly. How quickly should I stop? Like 1 minute or 2 minutes?
2 minutes.
2 minutes, okay. All right, this seems like a complicated way of rewriting the relations, but it gives us the chance to do something new. So I'm going to choose a partition of the positive real roots for SLE hat into a set of delta 0 and delta 1. And this is convex. So the easy way to say this is it comes from slicing the positive real roots with a hyperplane, taking all the real roots on one side of the hyperplane and on the other one. And instead of these relations, I'm going to have the relations that if I have a bunch of red strands on the left that sum up to a root in delta 0, that is 0. And if I have a bunch of red strands on the right that sum to something in delta 1, then that is 0.
red, but you mean black, yeah?
Sorry, yes, black strands. Sorry, yes, black strands on the far left, so in particular to the left of the red. And here I'm looking at blacks on the far right, in particular to the right of the, sorry if I said that. So if I get delta 0 on one side, I declare that to be 0. If I get delta 1 on the other side, I declare that to be 0. Those of you who like stability conditions should recognize this as a stability condition type thing. All right. And note here, this is the special case where delta 1 is empty. And all of the positive roots are in delta 0.
But when you say stability condition, do you mean versions?
I mean,
Like,
philosophically, yes.
oh,
We can talk about how later. Just if you like stability, this should look familiar. Like this should look like a stability condition on the category of quiver representations. All right. So fix our usual kind of thing. Let mu be some highest weight. This highest weight is going to be the sum of the mi lambda i's. Subtract off bi copies of each simple root. And consider an element of the affine Weyl group. Then if I look at the block where I take mu and I multiply it by w in the Ariki-Koike algebra, then that should be equivalent to this variation of the KLR algebra, with delta 1 being the roots that are sent negative by w, and delta 0 being the guys that remain positive when acting with w. With the RoCK blocks being the limiting case where I choose a finite Borel and I take delta 1 to be the preimage of the negative roots and delta 0 to be the preimage of the positive roots. And I mean, of course, you'll note these things never have this form, but only finitely many roots are ever relevant. So eventually these sets are going to stop. Actually, like the differences are not going to matter. All right, and I had sort of thought of this a long time ago, but I never thought anyone would be interested in it. And then people started talking about this question of like, what would correspond to this RoCK block? And I think this is the answer, or at least an answer. In particular, I think this should be somehow equivalent to this work of Evseev, Kleshchev, which unfortunately I found very hard to read, so it's hard for me to confirm, but I think you should think of this as a Turner double for the Ariki-Koike algebra. So that's sort of a speculative thing, but I thought people here might be interested in it. All right, thanks.